Hi, this is Ed Koehler with Extreme Networks, and I'm here today to talk with you about stealth networking and encryption, how they contrast, but more importantly, how they complement one another to create a superior network security posture. But first, let's get some terminology out of the way. Stealth and encryption really equals two terms called steganography and cryptography, and these may seem odd. If you have a background in this, you may be familiar with them. Most people would be more familiar with cryptography. Steganography is a little bit more of an odd term, and we'll talk about the background for each. So let's talk about steganography first. It's basically the practice of concealing messages. Information or other within non-secret text or data. And this is the stuff that you'd see in the Hardy Boys or the Nancy Drew novels, or something a little bit more sophisticated like a Dan Brown novel. Steganography is as you can see, it's a fairly old term, late 16th century, and it has Greek roots. And basically what the concept is you're taking text or some sort of information, and you're basically hiding it. I'm going to give you two ancient examples. In ancient Greece, for instance, it was a common practice, particularly during the Peloponnesian Wars, to take a wax tablet, scrape away some of the outer boundary, and then inscribe the message you want to send on the wood backing, and then cover over the tablet with renewed wax, and then send it on. And then the receiver would scrape off the boundary, and they would be able to read the message. Another later example, perhaps more interesting, and this is more legend than actual fact, it's by word of mouth, is the fact that the Mongols used to take, and they would take a young boy, a young teenager, and they would shave their head, and then they would inscribe the message that they wanted to send, and then they would let the hair grow back, and then they would send the young adolescent on a caravan out to the destination, to one of the more remote khanates. Once the remote khanate received the young lad, they would shave their head, read the message, and then, of course, be able to communicate in that way in a hidden fashion across the Silk Roads. Not sure how true that is, but it's an interesting story. Now, as far as how this relates to stealth networking, basically what we're doing is we're taking a network, and the network is obvious. You're attached to it. You can see it before you. It's an RJ45 you plug into, and the network service is quite obvious. However, the rest of the infrastructure is concealed. So let's talk about how we accomplish that, and how Extreme Networks Fabric Connect provides really the modern equivalent of a steganography type of implementation. So the first aspect, and by the way, we're going to move from the upper left around the outer perimeter. Up in the upper left, we see that we have a simplified protocol plane. Basically, we use 802.1AH is the data plane, and then we use ISIS as the control plane, and then we have a service plane construct that sits above that describes the services that are transmitted at the Ethernet level. And it's important to realize that Ethernet is the transport mechanism. We do not use IP. We do not use IP routing. We do not use IP to establish the topology or transfer any data services. IP is still used within the infrastructure. However, it is really transmitted by Ethernet transport, which is the 802.1AH data plane. Now, the ISIS instances are synchronized through the use of ISIS as a protocol, and this creates a programmable link state database that's basically distributed across the fabric, so we don't have the notion of a centralized controller. Notice how there is localized MAC learning, VSN separation between the virtual service networks, and then also the separation between locally versus remotely learned MAC addresses. So this is an important differentiation, and it makes things like our poisoning and MAC spoofing to be much, much more difficult. And then note again that the ESP circuit-based service separation, and what we mean by ESP is Ethernet switched paths. If you take the Ethernet switched paths and basically make them contiguous end-to-end across the network. You have something called an ISID, or an individual service identifier, and these are the virtual service networks that we're talking about. So as you can see, this provides a very dark networking environment that provides absolute and total separation between services, and also services separation of the MAC learning environment as well. By the way, this is a defined standard, as you can see at the bottom of the slide. Now, what are the end results to this? Well, without hyper-segmentation, without stealth networking, you can see that we're really locked into campus VLANs, access control lists, perhaps some route policies in the middle and the core of the network. But really, at the end of the day, you've got fairly good visibility from a hacker's perspective into the network infrastructure. When we deal with Fabric Connect and the end-to-end ISID capabilities, hyper-segmentation effortlessly reaches across the whole network infrastructure, and the visibility to the would-be attacker is very much compromised at that point. As a matter of fact, it's only limited to the local segment that they're compromising. So here we're seeing that perhaps they've compromised a video surveillance system. They really can't get anywhere else. The segment kind of limits them, provides the ability to limit any cross-propagation or lateral movement across the infrastructure, and it basically creates a dead end for hackers, and it forces them to be much noisier in their endeavors. Now, cryptography is a different type of approach, and many people say encryption, but actually encryption is actually a process within cryptography, and we'll kind of clarify that in the next few slides. But the important thing to realize is that this is really the art of writing and solving codes. And interestingly enough, it's a fairly modern word. It was first used by Edgar Allan Poe in the short story The Gold Bug, and the word that was used was a cryptograph, and obviously the art that would be used to create the cryptograph would be cryptography. So fairly recent. Edgar Allan Poe was not too long ago. The important thing we can realize, though, is encryption can be used not only for data in transit, which is primarily what we're talking about in this discussion, but also used as data at rest as well. So your laptop can have an encrypted drive, many do. Your servers can have data encrypted. Encryption can be used in those forms as well. Typically, there always are the use of code or algorithms, what are termed as ciphers, to perform the encryption. These can be fairly simple. We could simply reverse the alphabet. So I could say, okay, I'm going to send you a message, and we just understand ahead of time that A is Z, Z is A, and you just reverse them. That's fairly primitive, fairly easy. What we're going to do is we're going to use Caesar's algorithm, or Caesar's cipher, as an example because it brings in the concept of a key, and that's an important piece that we need to use as well. But I'm going to use some fairly simple examples. We're not going to go too deep into this because it's important that you understand just the general principles. If you're curious, you can research this further on your own. So this gives us a basic look at the dynamic of cryptography. And as you can see, there are two processes. There is the process of encryption and the process of decryption. And then we have these symbols called keys. And you can see that we have asterisks on each side. I'm going to talk about the mechanics of how this works. Now, Caesar cipher is basically what's known as an offset algorithm or a shift algorithm. That's the algorithm or the code that we would use to perform the encryption. So we're basically both understanding that we're going to do some sort of shift in the alphabet, and what we need to do is communicate what that shift is going to be. So in order to do that, we need to have some other algorithm which will determine the key that we're going to use to tell each other what the offset is going to be. So let's use a real simple example. I could send you a text message, and it could be two sentences. Hey, how are you? And then you could respond back with two sentences. I'm okay, and you? And now we've agreed, and that establishes what is termed as a nonce. Okay, that's the understood offset. So, okay, everything's going to have two added to it. Now what I can do is I can send you a text message with three sentences. It could be anything. And these are plain text. Now you know that you would take 3, add it to 2, and my offset is going to be 5. So everything I'm sending you will have an offset of 5. And basically the same thing happens with you. You send me a return text, we could be talking about a baseball game or anything. It can look fairly innocuous, and you could have 5 lines in your response. Now I take 5 and I add it to the 2, the nonce that we've established ahead of time. Now I know that your offset is going to be 7. So everything I send you, A is going to be E and Z is going to be D. Everything you send me, A is going to be G and Z is going to be F. And then we use that key, that understood key, 5 and 7, on each side to basically understand the offset that we have to attribute, and this allows us the process of decryption. So this is a very, very simple example. You can clearly understand that we have an algorithm for the encryption itself, which is the basic theory of offset, the shift algorithm, and then we have a separate algorithm which we're using to do the key generation. Now, obviously, these algorithms become very, very sophisticated in the modern world. We're not going to go further into details on that. Just the important thing is to understand the concept. What we really want to focus on is the use of encryption and how it can work with Fabric Connect. So first method is obviously link or trunk level encryption. And this is basically where we're establishing a network-to-network interface link between 2 Fabric Connect nodes. And we basically use something like MACSEC, although in branch office type implementations where we have to go over a WAN, we can use something like IPSEC, where we're basically encrypting the whole trunk. And we're saying everything within inside this network-to-network interface is encrypted. This is a fairly easy to understand mode. Most times we're using some sort of symmetric keys that are understood ahead of time and distributed. And this works very, very well. Most times, however, if you're using MACSEC, you need to be aware that the node has to, from a hardware perspective, be capable of doing it because it is a process that happens at the PHY layer. Therefore, it is hardware determinant, whereas IPSEC could be driven by some sort of software engine in order to accomplish similar methods. Now, another concept is the use of service level encryption. This is where we say, okay, I may have 100 ISIDs, but only 20 of them need to be encrypted. At this point, we can actually do services of individual encrypted ISIDs, and we have established partnerships, and we're actually working on service extensions on our own to provide this capability. And then finally, we can look at individual client level encryption, secure web type applications. So, like a secure web proxy or a VPN, like a VPN gateway. And in this instance, we have a PC with a VPN client or a secure web browser, and they're basically using encryption up to that actual secure web proxy or the VPN, and the traffic is embedded. At this point, you could have multiple levels of encryption. And the important thing about that is that we have to realize that they are not mutually exclusive to one another. So a great example of this is where we show MACSEC at the key core sites. We're using service level encryption with a partner that we have in the way of Senatus to extend out to certain non-MACSEC sites. And then we're using IPSEC out to the remote branch WAN sites. And you can see that we have an end-to-end encrypted footprint. We have 3 different methods that we're using, but really end-to-end we're providing encrypted services over the Fabric Connect environment by the combination of these technologies. Another great example is we run into this with in many multi-tenant and particularly government type institutions where you have a common secure MACSEC domain, but then each individual agency may need to have separate encrypted services. And this is where, we can use service level encryption or other methods of encryption, such as IPSEC or VPN, WireGuard, things of that nature inside the actual secure MACSEC domain to do proper separation of services at a cryptographic level. So encryption comes in many forms, but the big thing to remember is that encryption and stealth networking are vastly complementary. I hope I've shown that to you now. I'm listing some methods. Again, this is not a detailed list, but it does show some of the ones that are known to work. And basically any VPN solution that uses encryption can run over the Fabric Connect environment. And all of these methods can and do work in tandem with Extreme Networks Fabric Connect. And it really provides for the perfect combination of steganography and cryptography. So I hope this was entertaining, and I hope it was helpful. This is Ed Koehler with Extreme Networks signing off. Have a great day.